Hi, this is Preston Culbertson. I'm here this week with Lab 9, which is modeling 2D spring motion. The purpose of this lab is to model the motion of a spring moving in 2 dimensions from given video data. And my main results were 1, a working model of the system, and 2, I applied the energy principle to calculate the spring energy as well as the total change in energy of the system. So this week we were given a video of Dr. Greco releasing a spring from rest and allowing it to move in 2 dimensions. I put this video into Tracker and analyzed its motion using the software. I treated the spring as a point mass and tracked its motion over time, and I also placed the origin of the system at the base of the spring. So now I'm going to take you through my model. My model I built in VPython. My initial conditions were 1, the position of the mass, which came from the video analysis. I also used a few constants, such as the gravitational constant, which is given, and then also the spring constant and the initial length of the spring, which we calculated last week in lab. Then I took this and I calculated the forces on the mass over time. And so I calculated 1, the gravitational force, which is just mg, and then I also calculated the spring force using Hooke's law. I added these forces together to calculate the net force, and then used the momentum principle to solve for the velocity of the ball, and then also its position using the position update formula. So now I'm going to show you my model, which is this file, and so I'm going to run it. The orange ball will be my model, and the blue ball will be the data which I gathered from Tracker. So here goes. And so this graph here is the y position of both balls. So as you can see, we get harmonic motion moving in 2 dimensions, and the orange trail is the trail of my system. And so what we see is that the model works really well at the beginning. It matches really well. The periods are right on target. But then over time, the green, which is the blue ball's period, becomes longer. And the reason for that is energy lost from the system due to friction and air resistance. So now I'm going to answer the what does it mean questions. The first question is compare the periods of the x and y motion. And so what I did is in VPython, I plotted both the x and the y motion over time. Here's a picture of my x graph. And so what I did is I analyzed where at the bottom of these troughs, I analyzed where it reached the same value, and I calculated where, like how much time elapsed between those troughs. And so for this x period, I got 1.674 seconds, and then using similar analysis, I found that the y period was 1.530 seconds. And so the other question is, why would they be different? And so the reason for that is that there's actually 2 systems of periodic motion going on here. One is a pendulum of the x, which is moving back and forth, and one is a spring, which is the y motion moving up and down. So we actually have 2 different periods for the 2 different harmonic motions. So the second question is to determine the work done by the surroundings. So what was given is that we know our system is the mass, the earth, and the spring. And so what that means is that there's nothing left in the surroundings. So since there's nothing in the surroundings, work is equal to 0. And so then we know from the energy principle that delta E is also equal to 0. So we can calculate delta E as the change in kinetic energy plus the change in gravitational potential energy plus the change in spring potential energy. And we know that all is equal to 0. And the second question is the energy principle satisfied? And the answer is yes. Since we know that the work from the surroundings is 0, we know that the change in energy of the system is also 0. So the third question is, how does the change of origin affect the system? And so what the question asks us to do is to move the origin from this fixed attachment point at the end of the spring down to where the spring hangs at static equilibrium, which is about 0.7 meters down. And so I also did this in Python, and what we see is that before the move, all of the y values are about negative 0.7. They oscillate around that value. And after the move, all the y values oscillate around 0. And so what actually happens is that we can see that the change in y values is about 0.1 in this graph, and the change is actually the same, just with a different scale in this graph. So while the y position's values were affected, their change over time was not. We can also look at the energies before and after we move the origin. And so my key here is that the red graph is kinetic energy, the green graph is gravitational potential energy, the blue graph is spring potential energy, and the yellow graph is the total change in energy, which is 0 as per the energy principle. And so what we can see is that these are the exact same picture. They're from 2 different models, but the change in origin did not affect the energies at all. And so, again, while the y position values are different, the energy and forces stayed the exact same. So that's my lab 9. Thanks for watching, and leave any questions or comments in the comment section below. Thanks.